Okay, good morning, everyone. Today we're going to talk about part 3D, which is current research involving peptoids. All right, so over the course of this section, you've learned how to make peptoids, you've learned how to screen them, make large library of them, and so I'm just going to highlight a few examples in the literature where peptoids are actually being used, and it's pretty exciting. All right, so here are some examples of current research involving peptoids. So a company back in California, Chiron Corporation, Emeryville, in 1999, developed a peptoid termed CHIR29498 and others, and these were effective against a wide spectrum of bacteria, including some antibiotic resistant strains. So this should be effective. And I'll just give you the structure of this peptoid. I wouldn't expect you to memorize this or anything like that, but I just want to have you guys appreciate really how simple peptoids are, or how simple they can be in terms of their synthesis. And here we have sort of this hydrophobic portion on this side. Yeah, so that's what it looks like. So this was very effective at fairly low concentrations. So new antibiotics are of course important because antimicrobial resistance is an ongoing concern. New diagnosis for Alzheimer's disease. Okay, so Alzheimer's is characterized by brain plaques, and this often results from proteins that aggregate and form these insoluble fibrils, and this can lead to things like memory loss, and then it can lead to deterioration of the brain and coordination in the body. So Thomas Kodatic, a researcher in the United States, identified 3 antibody binding peptoids which could identify patients who have the disease with 93% accuracy and requiring only a simple blood test. So currently there isn't really a good definitive test for Alzheimer's other than meeting perhaps with a neurologist and undergoing some tests, right? So there isn't a simple way to characterize this. However, it has been shown that patients in Alzheimer's typically upregulate an antibody called IgG. Okay, so what is an antibody? So antibodies, are these molecules here that essentially have high affinity for particular, it can be other proteins, or it's part of our immune system, so they can attack invaders. So IgG antibody is one of the antibodies that is upregulated in Alzheimer's. And really the goal is to find a peptoid that is specific to IgG in the blood plasma. Okay, so the idea is that if you took a blood test from a potential patient and they had upregulated IgG, the IgG would bind to a peptoid or something tightly, and then you could use something like a secondary antibody to detect binding. So here you would have your peptoid. If IgG binds because of a peptoid or whatever you have to pull it down, then when incubated with a secondary antibody, you can add fluorescence antibody to that IgG, and you can see an increase in fluorescence. So you should be able to see lights or some type of signal immediately in that blood test. So it's very similar to like a Western blot. Okay, so yeah, so here you can see the disease. This is the IgG antibody. There's a lot of it. Okay, so you're going to have much more of that compared to a normal patient. They just characterize that with the purple color, just so you can see that. So how do they make this little peptoid library? So this is really, really quite interesting. So they use the same polystyrene beads that we've learned in class, and then they did that first amide bond coupling, and then with like a halogenated acetic acid with carbodiamide, DIC, and then they took this and then they did their alkylation, just like we learned in class, and then they repeat this over and over again. So what did they generate? So they generated on this bead here, they generated, first they put in a thiol, and then they generated peptoids, an 8-mer peptoid, and they had 1, 2, 3, 4, 5, 6, 7 different reagents and 8 different positions. Okay, so on paper it doesn't take up a lot of real estate here. It's quite small, but the total number of different compounds is astonishing. Okay, so 7 different reagents and 8 different spots. So you put that to the power of 8, and if you punch that into your calculator, that turns out to be around 5.5 million compounds. Okay, and it's remarkable because all you need are 7 different reagents. So they generated a large library of 5.5 million compounds in a relatively short amount of time. And then what they noticed was that 3 peptides were actually pretty good. This one here that I'm showing here is called the AMOG P3. Okay, so you can see it has this decorated motif here, and this here actually has very good and high binding affinity to the IgG antibody. And what I'm just showing you here in the bottom is some mice that have upregulated IgG, and these mice that exhibit this upregulated IgG exhibit increase in intensity and fluorescence when bound to this peptoid, indicating that it actually is working within that system. Okay, so that's one example of using peptoids. Another example is using something called Nano Rope. It's actually kind of interesting. It literally looks like rope. It's a self-assembled type of system, and it's really made up of different helices, and these can be engineered to have different lengths and different sequences. And the possible uses of Nano Rope is that it could be used to scaffold nanoscale construction, for example. It could be used for drug delivery, molecular sensors, sieve-like devices. So you could use it for medicinal chemistry, but it could also be used for things like material science. So how do they make these nano ropes? So the nano rope actually is comprised of these peptoid helices, and it's actually really quite simple. On one hand, you have this group here, which is a sort of a negatively charged carboxylate. And then on another helix, you'll have this blue group here, which is a NH3 group, which becomes protonated under physiological conditions, that's positive. So you can see that you have hydrophobic groups interspersed with polar ones. They arrange themselves in such a way to put the polar groups on one side and then the hydrophobic groups on one side. And furthermore, the positive charge will be attracted to the negative, so you can start generating these like nano-like sheets where you get the polar groups together on one face and then the hydrophobics on another face. And so peptoids are really good at making these nanostructures like nano ropes. You could even think of altering some of these hydrophobic groups with different ones to give it new structure-activity relationships. So you could play with that a little bit to see what types of different ropes and structures you can make. So anyways, I just want to highlight just some examples in the literature with peptoids. Okay, see you next time.